gully control works and sunken pits within the gully. This is the bed of the gully, this is the bank of the gully. The flow is like this, and in order to reduce the erosion within the gully, stone checks were constructed and they are called as rock-fill dams. In the earlier years, these were predominantly constructed in all the gullies throughout Andhra Pradesh as well as in peninsular India. The idea is that the flow in the gully, which was causing certain erosion, will have to be reduced in velocity, and such reduction in velocity would reduce the erosion in the bed and sides, and therefore a rubble fill dam or rock fill dam of this type would be needed for those functions. When this rock fill dam is constructed with rubble stone, then whenever a flow occurs, it has to pass through the various crevices of the boulders and rocks, and therefore the velocity of flow gets reduced, and when the velocity of flow gets reduced, then siltation occurs. This is the silt. So this siltation would be occurring depending upon the type of terrain and gully in a matter of 1 year or 2 years or 3 years. So when this siltation is formed up to the top of the rock-fill dam, then the people would be under the impression that the rock-fill dam has performed very well and it has served its purpose. But actually the real trouble starts after this siltation. Now let us study that. For example, when it is already silted up after a year or two, then even a small flow occurring in the gully, it would overflow as shown here over the rock-fill dam, and because there is an apron here, the rock-fill dam is quite safe, and this drop of water would in turn increase the velocity and results in forming scours along the bed of the gully. So after a few years, this soil will get eroded here and as well as downstream, because in addition to its natural velocity, it gets increased on account of the drop, and this drop will cause an erosive velocity scouring the soils. So after the construction of the rock-fill dam, we find a very interesting phenomenon of scours occurring on the downstream side and deposition of silt on the upstream side. Now in a situation like this, though there are no scours in this portion, there could still be scours here, and the scours would get intensified on the downstream side of such structures. So the problem of reducing scours or reducing erosion of gully is not solved by having such rock-fill dams. However, the problem can be solved by providing such RFDs close to one another. That means the top level of the lower down RFD is at the apron level. For example, another RFD will have to be constructed here, keeping the top of the RFD, that is this is the top of RFD, the top of the RFD at the same level as the apron level. Supposing another RFD is constructed here, then it will form siltation. Just as it has formed siltation here, it will also form siltation here, and series of terraces will be formed. Unless series of terraces are formed, these RFDs do not work satisfactorily. To form such terraces, series of terraces, it requires huge number of such RFDs, and these RFDs usually cost around 2000 rupees each or 2500 maximum. So when we have to construct these RFDs in large numbers very close to each other, all the watershed money perhaps would be spent on RFDs alone, and it is not possible in a steep slope gully, especially what we get in the upland areas of Andhra Pradesh, where the gullies have steep slopes. We have to see the economy of it. So therefore, in practice, they do execute such RFDs at longer spacing, one here, another at a greater distance, and like that. In practice, it is done like that. It is not giving any benefit, as earlier pointed out. It results only in scours down below, because terraces are not formed one below the other. In a situation like this, there is an economical way of handling the problem and reduce the scour and erosions, and also simultaneously increase the recharge component to groundwater. For example, in doing these structures, is there any increase in recharge to groundwater even if we do these structures close to each other, one below the other, as per the earlier technical recommendation, keeping the top of the lower down RFD as the same as apron. Suppose we do like that number of such RFDs. There is no increase in the groundwater recharge, water flows. Only thing is erosion is avoided. But now we can think of an economical alternative under the four waters concept. The economical alternative to reduce the velocity, to reduce the erosion, and again increase the deep percolation to recharge the water table. We will come to the next drawing how it is done. Earlier we were constructing all the past several years in a gully like this, a rock-filled dam like this, and we already discussed about the features of this and the problems on account of such RFDs. Now, as an alternative to this RFD, the device to reduce the velocity as well as increase the deep percolation is possible by having sunken pits in the gully, sunken pits in the gully bed. For example, this is the gully bed. We have a pit here. The details of the pit is 1 meter depth and 4 meter length at the bottom, and it will have 1-to-1 side slopes. And another sunken pit at a distance of about 4 to 6 meters, and yet one more sunken pit. Like that, the sunken pits will be excavated all along the gully. In a first order stream or a second order stream, we can execute about 20 to 40 such sunken pits, and the water, as it flows in the gully, it enters the sunken pit, fills up and overflows and goes through a silt trap, and again overflows over the silt trap and goes down to the next sunken pit. It gets filled up. Like that, the water flowing down will fill up all these sunken pits. Because there is certain storage created in these sunken pits, the discharge gets absorbed in these sunken pits. The discharge, therefore, in the Vagu, in the gully, would get reduced. The discharge in the gully, first order stream or second order stream, would get reduced on account of interceptions of the flows through such storages. And when the discharge gets reduced, the velocity also gets reduced according to the well-known Manning's formula. Given a slope and a cross-section area, if the discharge gets reduced, the velocity gets reduced. On account of reduction in velocity, there would be less scour or there would be no scour. So in this method, we have the storage as well as reduction in discharge. A flow which was something like this would get reduced to this type of flow at lesser depth, and therefore there will be lesser velocity and therefore lesser erosion. So these sunken pits will have to be done in the first order and maximum in the second order streams, and they should not be done down below where the third order streams or fourth order streams come up, because there the bed width will be more and there will be sand deposition, and it would be impractical to construct such sunken pits in the gullies. Also, these sunken pits should not get filled up with silt if there is an erosion. To facilitate the silt collection, a small silt trap is constructed on the upstream side of this sunken pit. Here the silt gets filled up in the trap and it overflows. The farmers on the side of the gully can take away this silt and use it for their lands. Usually the farmers convey tank silt to enrich the fertility of their rain-fed lands, and when the fertile soil is available in the shape of silt next to his field, he would necessarily on his own will try to collect that silt for enriching fertility into his land. So this silt trap may be needed, one for 2 or 3 pits depending upon the type of soils in that area. And as seen in the plan, this is the Wagoo course or first order stream or gully, whatever we call it, and this is the first pit, the second pit, third pit, like that as seen in the plan. There is a silt trap introduced here, and water as it enters, like as it enters, it requires some revetment, otherwise this slope will not be stable, it will get eroded. So to see that this slope is stable, revetment, rough stone revetment is provided as shown here. This is the revetment, and as it fills, it overflows. So there is no need for revetment here because it only overflows as it gets filled up. So we avoid the revetment here as well as in the bed. We have only revetment at the entrance side and for a small toe. And another important aspect with regard to the sunken gully pits is, at the head of each Wagoo course, we have to construct a mini percolation tank. That means when flood water enters the gully, if there is no storage of the flood water through a mini percolation tank, then that flood water will cause deposition of silt in the sunken pits and cause also problems of erosion near the sunken pits. In order to prevent the silt deposition, the first order streams wherever such sunken pits are constructed should have as a mandatory requirement a mini percolation tank on the upstream side. Sunken pits should not be constructed without a mini percolation tank on the upstream side. By mistake, in some areas I have seen, the farmers thought that they can construct the mini percolation tank later on, and they excavated the sunken pits, and they could not execute the mini percolation tank in time, and therefore when the rains came, it resulted in deposition of silt here and scours in the sunken pits. This is the sectional elevation taken across the sunken pit, and this indicates the Wagoo bed level like this, and the ground level on the banks like this, and the flow in the gully in this manner. Now this is a sunken pit excavated below the bed of the gully to a depth of 0.9 meters, and the length at the bed bottom of the sunken pit is 4 meters and a slope of 1:1, which means the length of the sunken pit at the bed level of gully is about 5.8 meters. And there is a small silt trap of 0.3 meter depth on the upstream side of the